Okay, the first handful, the first four, I believe, are very similar to the ones that we did yesterday in class. So if you struggle with those, please go back and watch the two videos from class yesterday. There's also videos there that are from last year that use different points, and hopefully you can work through those first four using those coordinate proof ideas that we talked about yesterday. This one here, okay, is asking you to make an argument about segments. Okay, and you know absolutely nothing about segments, right? But you know a lot about what in this picture? The angles. Can you find this angle measurement here? Yes. Okay, it's a linear pair, right? So now you got two angles inside the triangle. Do you automatically know the third one? If you have all three angle measurements, can you compare sides if two of them are equal? So you're going to find out that there's two angles in here that are equal. You should be able to look opposite and find the sides that are the same. Is that okay? All right. Key thing here, what do you know about these two lines here? They're parallel. That's going to be huge in being able to answer that question there. What about, that one's very similar to that first one. I think a lot of people are struggling on this one. Obviously, the concept, it's 4-5. We're talking about isosceles triangles in this section. And do we have an isosceles triangle in this problem? Yeah. Now, it's not the only theorem, though, that's occurring, and that's going to be something that we see a lot of, is that we might see one theorem that we're concentrating on. There might be 3 or 4 other theorems that we've used previously that we might have to target and use to progress through the problem. Okay? So, if this is 42 right here, what's this angle here? 42. That's the isosceles triangle theorem, right? Okay. Now, another theorem that we can use is if that's 42, that's 42. Can I use the triangle angle sum theorem to find that angle? Okay. I'll let you guys do that on your own. Not that hard. Okay. So we know what that angle measurement is. Okay. Now, my next question, because we got to start targeting X somehow, is this. I hide that, and I hide that. Do we ultimately get a picture that looks like this? Okay. And is this angle right here that angle? That makes sense? And that angle is made up by two smaller ones, right? So could I say X, so this angle right here is X plus 12 plus whatever that red number is. Does that make sense, everybody? How does that relate then to that angle, really big, and that angle? This, what kind of, is this is this angle here, this red one I just, is that an inside angle or an outside angle? It's an outside angle. What's a better word for an outside angle? Exterior. It's an exterior angle. What are these two angles called in reference to that exterior one? Remote interior. What do we do with the exterior angle and the remote interiors? We take those two, add them together, right? And that should equal this one, correct? So over here, should I be able to add those two expressions up? Set them equal to whatever that expression ends up being? And now I have the ability to solve for X. Okay? One of the, so there's 3 theorems in there, right? 3 theorems in that problem to address how to get a relationship for X. What a lot of people are wanting to do is say that X plus 12 is equal to 42. Because they're seeing that angle right there, and they're seeing that, oh, it's alternate interior with that one. And that is 100% true. They are alternate interior. But are they congruent? What has to be true in order for alternate interior angles to be congruent? These lines had to be parallel. Do we know them to be parallel? Nope. They look like it, but you don't know for certain. Okay, so we don't want to make that conclusion. Is that something we can do? All right, so let's say this. Let's say, I don't know what x ends up being here. Let's say x ends up being 10. Okay? If x is 10, will this angle be 29? This angle here would also be 29. Okay? So that would be, what, 58 degrees that I've used so far? Okay? So would that make this 122 degrees? That makes sense? This angle here would be 22. I'm going to tell you that's 96 if you go through the word. What's the relationship between those three angles right there? What should be the relationship? They equal 180. Does 122 plus 22 plus 96 equal 180? No. So is 10 my answer? No. But do you see how we can use other geometry that's present inside the problem that I never use to target my value of x? Never use those three angles adding to 180 to solve for x. But I can use that relationship to see if my x is right. Does that make sense? Okay. I think just throughout all math, not just geometry, being able to do stuff like that and recognize how I can use the information I've just found, what I think to be right, somewhere else in another theorem or another concept to prove whether what I think I did right was correct or not. I think it's a very, very important skill to try to develop. Okay? It's going to allow you to navigate a lot of algebra and a lot of higher level math a little bit easier if we can realize that and hopefully develop that skill at the 9th, 10th grade level. I'm just going to tell you with this one, I'm not going to go through much of this one. Draw a picture. Draw a picture and you should be well on your way. Now, it asks you to find LK, right? Are there any expressions up here that are written LK equals whatever? No. But there is the idea that HI and LK are congruent, right? So through the use of HI, I can find LK. So draw a picture there. Number 10, I think we talked a little bit about that yesterday in class. Okay, I don't think number 10 is going to be one that is going to provide too much trouble for you guys. Okay. Keep working on it. Like I said, it's going to be due Monday. I think some of you are seeing that you're only getting one example or one exercise on that, right? I sent that out in the email, explaining the assignment. The reason I do that, if you look at all these, they're instructor created, right? Okay. Well, if I get this wrong, it's going to give me feedback. There's no way for me not to provide feedback. Does that make sense? I wish it wouldn't give feedback and you could get it wrong 2, 3, 4 times and not know what the answer was. Does that make sense? But once you get it wrong, it gives you feedback and tells you what the right answer was. Well, then when I hit similar exercise and it generates the exact same question, you can all get 100s, right? Not having a clue on what you're doing, okay? So that's why instructor-created questions are only one opportunity per question, okay? Not trying to be a jerk or anything like that. That's, I mean, byproduct, but that's the reason why you only get one exercise on it. All right, so that being said, guys, I want to, and we keep working on that, keep asking questions about those things, but now that you have that little bit of insight, maybe you can plug away at those a little bit more tonight, and maybe if we need to, we can address some of those in a little bit more detail tomorrow. I want to get into section 4.6, which is the last section that we're going to concentrate on in this chapter. The last two sections are actually, we skipped one section, I think it's 4.4 maybe, and we're going to skip 4.7, but we're really not skipping them because I've kind of taken the information that was in those and we've already dealt with them inside other areas, other sections. Okay, so like one section was using corresponding parts of triangles. I think that's like it might be section 4.7 or 4, I don't know, 4.4, whatever. We've already been using CC, right? There's an entire section devoted to that. We've already talked about that. We've kind of integrated that into other sections, so that's why we're skipping it. This is exactly what we've done. You guys remember talking about side, right? When we first talked about side, and we started talking about how we got to write some congruencies in the left-hand side of our proofs, and if we write them in this manner that we get 3 sides congruent to 3 sides, that's going to yield congruency. And then when we get congruency with triangles, we can use CP, right? It kind of set up a structure of all our other theorems and postulates like SAS, AAS, ASA. They all kind of follow the same approach, right? It was just different components that work together to provide the congruency. This is just another one of those, okay? So there's really no new procedural thing. It's just knowing now a new recognition of, okay, if I have these congruencies, these types of parts congruent, that also leads me to congruency, okay? So we're talking about this, this theorem that we're talking about today only works in right triangles, okay? So how do I know if I have a right triangle? Okay, I got a little box in that angle, right? But what's that little angle, what's that little box mean? It's 90 degrees, it's a right angle, right? So by definition, a right triangle is a triangle with a right angle in it, right? So when I want to use this theorem today, the first thing I have to do is say that I know I have right triangles, okay? And we know we have right triangles by identifying a right angle within those triangles. Right now, really the only kind of ways that we can know that we have right angles is if they tell us, or if they tell you you have perpendicular lines. Those are the main techniques for determining whether we have right angles inside our proofs. And there might be a couple others that we see eventually. Those are the main approaches. Okay. In order to address the theorem that we want to talk about today, there's some vocabulary used in it that we want to make sure we're all on the same page with. The first one is hypotenuse. Hopefully you guys know what a hypotenuse is. I've had some people not know what a hypotenuse is in the last couple of periods. Should be something that we learned in like the 5th, 6th grade, right? Okay. You learn it to be the longest side in a right triangle, correct? Why is it the longest side in a right triangle? It's always opposite the 90 degrees, right? And we talked in section 4.1 that across from the largest angle is always the longest side, right? Is there ever an angle larger than 90 in a right triangle? No, okay? So that's why the hypotenuse is always considered, you probably defined it in previous courses as the longest side of a right triangle, okay? That's fact, okay? But it is the side opposite your right angle. Only right triangles have hypotenuses, okay? An equilateral triangle does not have a hypotenuse, okay? An isosceles triangle might have a hypotenuse if that isosceles triangle is a right triangle. Does that make sense? Okay. But triangles that have right angles have hypotenuse. Triangles that do not have right angles do not have hypotenuses. Okay. And the reason I say that is because in the past, we'd be working with a non-right triangle, and somebody would tell me that that segment's a hypotenuse. So there's no way that can be. That's only a statement. It's only a component of right triangle. Okay. The other two segments, the segments that come together to make the right angle, are referred to as legs. Okay. Now we've also seen legs elsewhere, right? We've seen legs of isosceles triangles. Here, these are legs of right triangles. Okay. Down the road, in a couple chapters, we'll see legs of trapezoids. Okay. So legs is a common vocabulary word that gets played over and used over and over again. But we should usually put that of what after we say it. So legs of an isosceles triangle, legs of a trapezoid, or something like that. Does that make sense? Okay. Later on, chapter 5, this is what chapter 5 is going to be all about, is we're going to take triangles and start talking about certain segments that exist within triangles. We learned that the legs of a right triangle are called altitudes. Okay. So that might be something that you can kind of interchange with the word leg there for a right triangle. Okay, so we all okay with that? So this is the theorem. It's called hypotenuse legs. So hopefully you realize the purpose of knowing those vocabulary words. Basically what it says, I'm going to read it word for word, but if we see that, it says you say, if I have one hypotenuse congruent to another hypotenuse, hypotenuse of one triangle congruent to hypotenuse of the second triangle, and a leg of the first triangle congruent to a leg of the second triangle, that is enough to say that the two triangles are congruent. Okay? Hypotenuse leg. What? My day's always good. What is that? Not really either. I've never watched it. Sorry. Bumblebee. Huh? That's the only one I know the name of. What? Owl? Yeah. I don't know. My favorite movie? It's a toss-up. I like. You ever watch Tombstone? Tombstone's good. You guys know who Wyatt Earp is? Doc Holliday. The Shootout at the OK Corral. You ever heard of that? Western. Okay. Thank you. It's a really good movie. It's got Kurt Russell in it. Val Kilmer. Good movie. I like Good Will Hunting. Ever watch that? It's not about hunting. It's actually about math. It's actually about a very, very intelligent guy that lives in South Boston. It's got Robin Williams in it. It's got Matt Damon. It's got Ben Affleck. It's got Ben Affleck's little brother in it. Good movie. Kind of vulgar. I use a lot of bad words in it, but it's got a math background to it. There's what's another one? You ever watch Lincoln with Daniel Day-Lewis in it? Good movie. Those two movies are probably my favorite. I like Die Hard movies are good. I mean, if they're on, I'll watch them. I don't know if it's a good Christmas movie. All right, so now you've got that written down. This is what hypotenuse leg is. If I've got those two right triangles, and I'm able to show a hypotenuse congruent to a hypotenuse. Hypotenuse congruent to a hypotenuse. And I'm on the wrong page here, so let me. Hypotenuse congruent to a hypotenuse, and then a leg congruent to a leg. That's what you're going to be looking for inside your proofs or inside your algebraic problems that you have to develop congruency of triangles with or whatever. You're looking for that information to use hypotenuse leg. Okay? Now, think about this. Instead of using H and L, let's go through and see what that congruency would be using S's and A's. If I use S's and A's, would you agree you got two S's? Would you agree that the A, because these right angles are going to be congruent, right? Would you agree that the A is not between those two S's? So for my A that is not between those two S's, have we talked about that being an issue for us? Was angle side side allowed to be a theorem, postulate for congruency? No. Okay. Now the reason why that was an issue is because if you remember, I showed you this with GeoGebra a while ago. If I were to take something like that triangle is there, okay, and I just kind of take all the parts. So that part, so that's an angle, a side, and then that side right there, okay, and I start to swivel this, okay, I get one triangle. That makes sense? If you guys agree with those two triangles are congruent, okay, and I keep swiveling and I only get that one triangle, okay. But there was also a situation where maybe I take, see if I can do this, make it a little bit longer. I can take that same information, angle, side, side, and I can get that triangle there, but then I could also maybe get that triangle there. Does that make sense? Okay? So that's a problem. It's because I don't know which triangle I'm getting, so I can't guarantee that I'm going to get the same exact triangle, so I can't guarantee congruence. Does that make sense? Because there's a potential of two different triangles to be created. Well, if I'm working with right triangles, okay, and I swivel this thing through, If I swivel that through, does it make sense that that's really the only place that that C prime is going to show up? Does that make sense? And that's the only triangle that I can ever get. So I'm guaranteed that there won't be two triangles here, and there won't be zero triangles here. There will be definitely one, and it's going to be congruent to what I started with. Okay? So this is why it's a special case that angle side-side works, or side-side angle works, but because we don't want to develop the understanding or the thought that angle side-side or side-side angle always works for all triangles, we don't use S's and A's. Because S's and A's are the ones that we say that it doesn't matter what kind of triangles I start with, right triangles, non-right triangles, obtuse, acute, whatever. I can show those parts congruent as SSS, SAS, ASA, AAS, whatever. I can guarantee congruency. SSA, you cannot guarantee congruency unless it's the right triangle. So, because it's the right triangle, instead of using those letters S, S, and A, we use H and L. Does that make sense? So now it reminds us that it's a theorem in which I need those parts. It's basically telling me that side-side angle works only in right triangles and not all triangles. Okay? So to eliminate the confusion or the desire to say that this works in other types of triangles, we don't use those letters. We use H and L. And the H tells us hypotenuse, the L tells us leg. So hopefully the word hypotenuse tells us it has to happen in a right triangle. Is that okay with everybody? Okay. Just trying to get you to understand why they don't call it SSA, because we're trying to eliminate confusion. All right. So it's the exact same thing we've been doing, guys. When we do a proof, we're going to try to get these parts that are inside this theorem to show up in our statement. We're going to try to show hypotenuse is congruent to hypotenuse. We're going to try to show legs congruent to legs. Okay? And if I can do that, then I've got enough to show the triangle congruent. I got enough to get to my conclusion of my theorem. That being said, if I want to use hypotenuse leg, this is just a personal belief. If I'm going to use hypotenuse leg, okay, I'm going to tell everybody in my proof that I've got right triangles because I want to make sure that I think it's kind of an indicator statement that if I write it down, it reminds me, oh yeah, I got this theorem that deals with hypotenuses and legs that is just working for right triangles that I have at my disposal. But if I don't write the statement that I have right triangles, I might overlook HL because it doesn't get used a whole lot. Okay, it's kind of infrequent in regards to its usage, but it is a tool that we can use. So I like to write the fact that I've got right triangles in my statements, and that reminds me I can use HL. So we're going to write our given down just like we normally do. And in this one, I give you a lot of the given. Okay, or I give you a lot of the components you need to get to congruency here. All right, so we've got these two angles are right angles, and an SP is congruent to QR. When we have triangles in our picture, we want to show, or usually we talk about if we have triangles in our picture, we want to try to show them congruent, right? So that's my goal here. I want to try to show them congruent. So if that's the task, every time that you get right angles, it makes sense, I think, to say that triangle PRS, because it has a right angle in it, right? I'm going to say triangle PRS is a right angle, or sorry, right triangle. And we'll say the same thing for RPQ. Because they have right angles in them, right? Okay. That's the step that I was saying that I think not every time that you do a proof that uses a hypotenuse leg or targets a hypotenuse leg is going to say that that's necessary. You might get through your homework tonight, and there might be some drop-down windows for some proofs that you use hypotenuse leg, but nowhere in your statements did you say you had right triangles. But there might be a couple proofs that do that. Okay. I think it's important because now that reminds me, oh, I got right triangles. We had a theorem that dealt with congruency of right triangles called hypotenuse leg. So it kind of gets the ball rolling for me that I probably going to have to use hypotenuse leg as my theorem. Okay. Why do I know that these are right triangles? Okay, because the box, because we got right angles, right? If I have a triangle that has a right angle in it, why do I know I call it a right triangle? What overarching statement says that when you have a right angle in a triangle, you can call it, you can classify it, you can categorize it, identify it as a right triangle? What kind of statements allow me to categorize, identify? Don't definitions do that for us? Definition of right triangles. If I look in the back of the book, is that going to say, when I look up right triangle in the back of the book, is it going to say it's a triangle that has a right angle in it? Yeah. Okay. So that's how I knew it was a right triangle. Okay. Okay. So now, we're getting the congruency they gave me. They gave me SP congruent to RQ. What is SP for that triangle, that right triangle on the bottom? On the bottom left. It's the hypotenuse, right? So they're giving you an H hypotenuse congruent to hypotenuse. They're giving you the H congruent to H and what you need for hypotenuse leg, right? Now I need a leg congruent to a leg. In my picture, what leg is congruent to what leg? PR. PR is congruent to PR. Reflexive, right? So my whole story that you're seeing that this proof is really no different than anything we've done already so far. Okay, with our other triangle proofs, very similar type things where we do reflexive. We look for other congruencies, that kind of stuff. Mark it in our picture. Okay. So now PR was a leg in the triangle on the left. It's a leg on the triangle on the right. You have now found a hypotenuse in a leg congruent to the hypotenuse in the leg, right? So when I get that, when I've met the criteria for congruency, we can now say the triangles are congruent. Okay? Let's say step 4, a triangle PRS is congruent to triangle RPQ. Reason? It's now HL. Those are the parts that you've shown to be congruent, right? Previously, that step was like SSS or SAS or something like that. Now we can use HL. All right. But like every other theorem that we've come across, if I'm going to use that theorem, if I'm going to use hypotenuse leg, which says you need a hypotenuse congruent to hypotenuse and a leg congruent to the leg, then you need in your statements, before you use it, you need in your statements that criteria to be met. And we've done that. Okay, so we know we're allowed to use it. Now, after that, if need be, could I say angle S is congruent to angle Q? Yeah. Now, what would my reason be? CP, CTC again, right? Okay. So all the other ideas that we've used throughout the course so far, or throughout the chapter with these triangles, is the same here. It's just a different or alternative way of showing triangles congruent. Only works with the right triangles. Okay. Cannot use hypotenuse leg with triangles that I do not know to be right. Okay. So let's do. I don't want to do. Maybe this one. Let's kind of maybe talk through this one and kind of maybe a paragraph type proof. Okay, maybe I'll type this out for you. Okay. Says BE bisects AD at C. BE bisects AD at U. What's getting bisected? Fred? Huh? AD is getting bisected, right? Okay. If Alex punches Mr. Fay, okay, who's getting punched? Mr. Fay, right? The person at the end of that statement. So when I say BE bisects AD, AD is the thing getting cut. Does that make sense? Okay. For some reason through the past and even today, when I ask that question, BE bisects AD, a lot of people want to say that BC is congruent to CE. We don't know that. Because BE is not getting bisected. BE is the bisector. It does the bisecting. It does the cutting. Does that make sense? Okay. So I want to write here, like I said, let's do a paragraph first. So kind of show you how we go about paragraph first. They're exactly the same as two comp proofs. but they have a little bit better flow. Okay? So DE bisects AD. So I'm going to say DC, sorry, AC. AC is congruent to CD because of the definition of a bisector. Okay? Now, if I get to this, AB is perpendicular to BC, right? AB is perpendicular to BC. AB is perpendicular to BC. What does that give you? Okay? Okay. Oh. Would you guys agree that? Okay? AC is here to CD because of the definition of a bisector. And angle B and angle E are both right angles by the definition of perpendicular lines. Does that make sense? Okay. Can you see that AC equals CD by the definition of an angle bisector would be like one of your first statements in your statements and reasons in your two-column proof? And then as I'm working through and I find the perpendicular statement, AB is perpendicular to BC. On the left-hand side, I say angle B is a right angle. And on the right-hand side, I would say because of perpendicular lines, definition of perpendicular lines. So I keep doing it. So every time I write something in a paragraph form, essentially each statement I write, I'm going to follow it up by its reason. Okay? So every statement on the left-hand side in my left-hand column of a two-column proof is going to then be followed up by the reason in the right-hand column proof. And then all I do to go from statement to statement is I throw in words like this. You guys know what those words are called? Transitions. That's exactly what they are. Okay? So therefore, so if B and E are both right angles, therefore triangle ABC and triangle ABC, if I call the other one DEC, are right triangles by the definition of right triangles. Does that make sense, everybody? Okay. All right. So provide. Now I don't have my given in there, but I should probably write. In addition, if AB is near the DE, that was given, right? And those are your legs. Then the two triangles, ABC and DEC, are congruent by hypotenuse leg. Because at the beginning, when I said AC is near to CD, isn't AC and CD, aren't those my hypotenuses? Okay. So that's a way for us to show a proof through the use of a paragraph. Okay. But if we were to take sentence to sentence apart, okay, the first half of each sentence would be a statement on the left-hand side in our two-column proof, and the second half of our sentence would be our reason on the right-hand side of our two-column proof. Okay. But you guys see how, you know, this is really no different than the last proof, except for the last one they blatantly gave me right angles, right? They told you these two angles are right angles. Here, do they hide that in vocabulary? They hide it perpendicular, right? And the last one they gave me my hypotenuse is congruent. They blatantly told me that. Okay. Here they hide it with the word bisect. Okay. And then obviously in the last one we were able to use reflexive to find the legs congruent. Here they explicitly give it to me or blatantly give it to me. Here's a question. What do you know about that angle right there where my cursor is, and this angle right here where my cursor is? They're vertical, right? Okay. So could you have added that in? Could you have used that? Yeah, if you're a person that says, I'm going to say these are vertical, you have an angle, and then a side. And over here, an angle, and a side. So you could have approached this proof without using hypotenuse leg. You could have used angle, side. Okay? And that's why I want you guys to recognize as you're doing things in mathematics, there's usually more than one way, right? Okay? Not saying you have to use hypotenuse legs. Sometimes, like in a course exam, might say, provided this picture, prove using hypotenuse legs. So if you're a person that uses angle, side, even though you got to the right proof and you validated the argument, you've done it wrong because they tried to structure it for you. Does that make sense? Okay? Just kind of pay attention to those things. Here's a question. This is the last statement. Okay? If I told you BE bisects AD at the beginning, that's what we found out, right? BE bisects AD. You now found out that these two triangles were congruent. And now what can you tell me about BC and EC? They're the same. BC and EC are congruent. What do BC and EC in their names share? C. So doesn't C have to be a midpoint between B and E? Okay. So AD passes through BE's midpoint, right? So is AD also going to turn around and bisect BE after I've shown these two triangles congruent? Yes. Okay. Now we didn't know that at the onset. We couldn't say that at the onset. We actually had to show the triangles congruent and use CC, find that BC is congruent to CE, but then we can turn things around and say, yeah, now AD is bisecting BE as well. Okay. Does that make sense, everybody? All right, so I've opened up 4.6, which is going to target hypotenuse legs. I've opened up 4.5, coordinate proofs, which was open yesterday for you. And I've also opened up 4.5, the worksheet that's sent you in an email that is just strictly kind of algebraic problems with isosceles triangles. And all of those are going to be due on Monday. Okay? So give you a little bit of time to work on those. That worksheet, when you're getting your answers finished on that worksheet, you can go into Math Excel and you can type those in to the template that's provided in Math Excel. And I will send out an email. I'll talk about it again tomorrow and the next day, but I'll send out an email to remind you if you're confused on what you need to do with those assignments. They're all due on Monday. Now, test is on Friday. So do not procrastinate. Now I'm just going to do all the homework on Sunday. Because what's the number one tool to prepare for our test? Homework. To use the homework to allow you to practice, right? To get ready for it, to see questions that are going to be similar on your test. If you haven't looked at those two sections until Sunday, you're not going to expose yourself to the information that's necessary to be successful in the test. So make sure you look at it. I'm not saying you got to finish it all. The more you do of it, the better I think you're going to lift yourself up for that test. Yes?
So all the worksheet are all the answers, whole numbers?
I don't know.
You actually do know.
Well, I'd have to double check.
I think that's
You might. I mean, decimals and fractions are not illegal.
yeah.
I mean,
It's just we have
and that